So now with this, the idea in mind that there's a trade-off between how well the model fits and overfitting, I want to talk about various measures of model fit. And we're going to think about these critically, which is how you kind of have to think about them. And my goal here is for you to understand what the most common measures of model fit are and what they're really doing. So the most common one, or one that I want you to focus on, is called R squared. It's got to be a capital R squared. And first, I'll just tell you what it's equal to. It's defined in terms of things you already know. R squared is 1 minus the sum of squared residuals from the model you're considering divided by sum of squares total from the model you're considering. So you can think of this as the overall variability, right? SST measures the overall sum of square differences in your data points from the overall mean. And this as the residual variability from the model that you're actually considering. And you know that the residual variability from the model you're considering plus the variability within the model you're considering equals the total amount of variability. So another way to think about this is as sum of squares model divided by sum of squared total. In other words, R squared is the proportion of variability in the outcome variable that is due to the predictors in your model rather than noise. I'll say that another way. R squared is the proportion of variability explained by your model. I want you to know that I'm choosing this word variability carefully. I don't mean variance, right? This is not the a variance term divided by another variance term. It's not the proportion of variance. Sum of squared is certainly related to variance, but it's a ratio of sums of squares. So we know that these sums of squares are one way to measure variability, and R squared is the proportion of sum of squared total. That is sum of squares model as opposed to sum of squared residual, right? And again, just to be clear about where this is coming from, we said earlier SSW plus SSB equals SST. Well, remember that another term for SSW here could be SSR. Another term for SSB can be SSM. I'm switching which labels I'm using because I'm now talking about the convention for regression and talking about R squared, but it's exactly the same idea. So if this is true, then I can divide this through by SST, right? And then this is the thing that's equal to R squared. It's the proportion of variability in your outcome variable that is due to the model as opposed to due to noise. So clearly we want this number to be big in general, right? Putting everything else aside, it would be nice if R squared was big. Note that it can't be bigger than 1 because it's a proportion, right? We know that the sum of squared model can't be bigger than the sum of squared total. What I'm going to do is list some facts about R squared. Things that are good for you to know. So the first thing for you to know, this is something that's very helpful about R squared. It is possible to calculate R squared. You can calculate R squared from a linear regression model with any number of predictors. As we add predictors, it's harder to figure out what model might be a good idea, right? Like you can't just make one simple scatter plot. You can't just look at the slope and make a judgment, look at one slope coefficient and make a judgment. There's more than one p-value in your table of coefficient estimates, and those are hard to interpret sometimes. So the fact that R squared is a quantity that will measure the proportion of variability in your model, a portion of variability in the data that's due to your model, no matter how many predictors you have, that is a really helpful thing. So that's a very, very positive. Let's say predictors or terms, because you could have, as I did in a previous video, have maybe just one predictor variable, but then include it squared, the same variable squared, the same variable cubed, etc. And that's what that's what's possible here as well. So that's one fact. Here's another fact. If you do have only one predictor or term, one predictor slash term. In other words, if you're thinking about a simple linear regression, then r squared is equal to little r squared. Remember that little r is the correlation. And we talked about correlation as this idea of measuring to what extent the dots were diagonal from each other as opposed to adjacent from each other when you make quadrants based on the sample means. So that's what correlation is. If you calculate correlation from a simple linear regression and square it, you will get the capital R squared. So in that sense, R squared is a generalization of correlation, right? If you have only one predictor, then reporting R squared is no more interesting than reporting correlation because it's just correlation squared. But if you have more than one predictor, you can't calculate a simple correlation. It just doesn't make sense with more than one predictor, but you can still calculate R squared. So both these first things are nice, right? It's nice that R squared can be calculated with any number of predictors, and it's also nice that it is just a version of correlation when you have just one predictor. Here's something that is really important to know, but less helpful about R squared. R squared increases, or at least doesn't decrease, every time a term is added to the model even if the term is not useful. So this is important, right? Suppose we're thinking about a context with lots of variables that could matter. So if I'm trying to predict people's incomes and I include their job field as a predictor, right, we'll get a certain R squared. Say I do that and I get an R squared of like 0.2. I'm making it up. But suppose that 20% of the variability in income depends on what field you work in. Right? That sounds not crazy to me. And then suppose I add to my model another variable that matters, like education level. So when you take into account both education level and field where you work, right, maybe now that's 35% of the variability in income explained, right? And then suppose you take into account how long somebody has been working since they finished their education, right? Well, it seems like that should be helpful for predicting income as well. So now maybe I'm just making it up. Maybe I'm now able to predict 47% of the variability in income based on these three predictors: job category, education level, and number of years working after education, right? So R squared goes up as you add useful predictors. But here's the thing. If you take that model and you add to it, like, let's think of something absolutely useless. Number of rolls of wrapping paper in the person's closet, okay? That will make R squared increase as well. Now, maybe you're telling yourself a story right now about why the number of rolls of wrapping paper might be related to income. So let's try another one. If that person puts some bean plants in the sun, number of sprouts that will appear, right? So if everybody in the study does the same little experiment at home, they'll each get like 1 sprout or 2 sprouts or 3 sprouts. If I include that number as a predictor for income, that will also increase the R squared. If I add number of Cheerios that the person's child ate from a 100-calorie pack of Cheerios yesterday, right? That also will increase the R squared. If I include an indicator for whether their shoelaces are black or brown, that will also increase the R squared. every time you add a term to your model, even if it's a term that is not actually helpful for predicting the outcome, R-squared will increase. So even if the term is not useful, R-squared will increase. What that means is you can't just choose the model that has the highest R-squared. Because you will for sure be overfitting. You will have a higher R-squared every single time you add a predictor to your model, even if that is not a good predictor. Now let's try to think about why that's happening. Well, remember that R-squared is the proportion of variability explained by your model, but it's 1 minus the sum of squared residuals. So here's the thing. If you add a predictor to your model, the residuals are not going to get worse. Like if I had that indicator for whether somebody's shoelaces are brown or black, the sum of squared residuals are not going to get bigger, right? Like your best guess at somebody's income is not going to get worse just because you included a predictor that was not useful in the model. So it can't get worse. There's no reason that would make it, that extra information would make things worse. Your guess at somebody's income will not become worse if I also tell you what shoelace color they have. But it could be that by chance, maybe there is, in the data set, some correlation other than 0 between shoelace color and income. In fact, it'd be shocking if you took a data set where you had people's incomes and you had their shoelace colors and you calculated the correlation and you actually got exactly 0. That would shock me. You'd probably get something like negative 0.02 or positive 0.01. And if you get any number other than 0 for the correlation between this useless predictor and the outcome, that will decrease the sum of squared residuals a little bit. And if you decrease the sum of squared residuals a little bit, then you increase R-squared a little bit. R-squared will increase every time you add a predictor to the model, even if that predictor is not useful.